Okay, good evening, everybody. And welcome to another online review session in organic chemistry. In today's session, we are going to discuss the chemistry of inolate anion. Specifically, we shall discuss Aldol condensation, Claisen condensation, and Robinson annulation reactions. I do notice here, I see Jaconda Kepas and Natalia Stepanova, they have joined us, so you are both welcome. Okay, to get our session started, Jaconda, go ahead and read this question for us.
Draw the aldehyde or ketone that the following enol could be prepared by the Aldol reaction.
Thank you. I also notice here that Ines Kifando has joined us. Okay, so this question is asking you to draw the aldehyde or ketone that the following enol, of course, an enol is the alpha beta unsaturated carbonyl compound is referred to as enol. Okay, so they wanted to give the aldehyde or ketone that the following enol could be prepared from using Aldol reaction. Now, this is the molecule right here. Okay, let me ask you a couple of questions here. Taking a look at this molecule here, they've already told you that this molecule is produced from an Aldol reaction. Now, the Aldol reaction, would that be a mixed Aldol reaction or a simple Aldol reaction? Just send me your answer through the text window. Will it be a mixed Aldol reaction or simple? Excellent. Mixed. Very good. You say mixed. Okay. Any other choice? Okay. About the rest of you, is it mixed or simple? Okay, I see. Okay, some people say as a simple Aldol reaction, and some of you say mixed. The correct answer here is it is a simple Aldol reaction. So let us go to my notebook, and then we are going to complete this question. Okay, so this is the molecule they have given us. Okay, what I'm going to do now, I'm going to write this molecule here, so we could see we could work on the problem together. Okay, so we have this aldehyde here, okay, and then we have the carbon-carbon double bond. You notice here, the carbon-carbon double bond is conjugated with the carbon-oxygen double bond, and of course that is why the molecule is referred to as an enol. Okay, anytime you have a carbon-carbon double bond and a carbonyl in a molecule, that molecule is referred to as an enol. In this particular instance, this enol is conjugated. In other words, you have only a single bond separating the carbon-carbon double bond and the carbon-oxygen double bond in this molecule. Okay, so let me go ahead and do this here. We have this here. We have the carbonyl of the aldehyde, hydrogen here. We have this here, carbon-carbon double bond, hydrogen here. And then we have this, CH2, we have CH3, and then we have this here, CH2, another CH2, and finally a CH3. Okay, what I'm going to do here, in order for you to to help me solving this problem, I am going to number the carbon atom in this molecule. I will call this carbon 1, carbon 2, 3, 4, 5, 6, and then I will come back here. I will call this here 7, and then 8. Okay, so you have 8 carbon atoms in this molecule. Now, this is the question I have for you. In this molecule here, which of these carbon will be your nucleophilic carbon? Which one will be your nucleophilic carbon? Which carbon will be your nucleophilic carbon? In other words, the carbon from where you generate the enolate anion. Number 3, okay, is that right? Number 3, how many people say number 3? Okay. Oh, number 2. Okay, good. Number 2 is correct. Number 2 is correct. Okay. So therefore, you guys say number 2. So this will be your nucleophilic carbon. Therefore, which carbon here will be your electrophilic carbon? In other words, the carbon that will attract the nucleophile, will attract the enolate anion. Okay. You say that is carbon number 3. That is also correct. Okay, so if that is the case, what you guys are therefore telling us is that we have to cleave this molecule. We have to cleave this molecule here, okay? So since you say this is your electrophilic carbon, carbon number 3, that means this is your carbonyl. And since you say this carbon number 2 is your nucleophilic carbon, that means this is your enolate carbon. Okay, so let us see, what does it look like? Let us do this. Okay, we have that. And then carbon number 2, we say that is this here. Okay, so we say this is carbon number 2. Your enolate anion is going to be here. Okay, so therefore we have this here, and then we have this. CH2 is here, and then another CH3 is here. So right now, let me go ahead and number those carbon. So this is carbon 1, carbon 2, carbon 3, carbon 7, and carbon 8. Okay, now let us go to this side of the molecule. Okay, this side of the molecule, let me use a different color pen. So this side of the molecule, you say carbon 3 will be your electrophilic carbon, so we expect to have a carbonyl there, right there, and then we have this here. Okay, and then we have CH2, and then CH2, and then CH3. If you look at this here, let me go ahead and take away the enolate carbon here and simply place the 2 hydrogen here. Okay? Take a look at this molecule. Once again, let me go ahead and number this. We say this is carbon number 3, based on what we have here. And this is carbon number 4. And this is carbon number 5. And this is carbon number 6. Okay? Now, let me ask you this. Let us call this molecule A and molecule B. Molecule A and molecule B, what is the name of both of those molecules? Can anybody give me the name of molecule A? What is the name? Okay, butanol. Excellent, excellent. Butanol, it is an aldehyde. So also, what is the name of molecule B? Okay, you also say butanol. Exactly. So therefore, you will see that molecule A and molecule B are the same, are molecules from the same compound. Therefore, the answer to what I asked you before was this must be a simple Aldol reaction, or a simple Aldol condensation reaction. Okay, because both the molecule that gives you the inolate ion and the molecule that give you the electrophilic carbon, they are from the same compound. So this is a case of a simple Aldol condensation. Okay, now do you want us to write the mechanism for this, or is this clear to all of you? If you want us to write the mechanism, say yes. If you want us to move on, just say move on. Okay, move on. Very good. Okay, very good. So therefore, the answer to this, both this here, molecule A and molecule B are the same molecule, and those are the molecules that gave us this molecule here, this Aldol condensation product. Okay, so we go to problem number 2. Okay. If your mic is working, can you go ahead and read this for us? I know Jaconda's mic is working, but anybody else, mic is working, can you go ahead and read this question for us? Okay. Okay, Jaconda, go ahead and read this question for us.
The following molecule was formed by an intermolecular Aldol reaction. Draw the dicarbonyl precursor that was used for this preparation. Okay,
very good, and thank you. Okay, by the way, I also want to welcome some of you who have just joined us. I see Don Payne, Kiara Bromfield. Okay, both of you are welcome. I also see Lorna Kumar. You are all welcome. Okay, now, in this molecule here, they say the following molecule was formed by an intramolecular Aldol reaction. Now they want us to draw the dicarbonyl precursor. Precursor simply means the starting material in this case that was used for this preparation. Okay. Okay, so let me go ahead and write this molecule here so we could dissect the molecule and do some analysis on it. This molecule is a 6-member ring molecule. You have a carbon-carbon double bond here, and then you have this. Okay, it's a methyl ketone. Okay, and right here you have a CH3. Okay, now let me go ahead and number this molecule here. I will call this, let us call this carbon 1, carbon 2, carbon 3, carbon 4, 5, 6, 7, 8, and I come back here, this carbon, I say this is carbon number 9. Okay. Now what they want us to do here is to give the starting material for this molecule. Let me ask you this. Okay, which of these carbon will be your nucleophilic carbon? You know this is an Aldol, intramolecular Aldol reaction. Which carbon will be your nucleophilic carbon? In other words, the carbon that will give us the inolate anion. Okay, okay, you say carbon number 3. Okay, let us see. Carbon number 3. Okay, how many of you say carbon number 3? Okay, carbon number 3. Okay, that is correct. That is correct. Now, which carbon will be your electrophilic carbon? In other words, the carbon that will give you the carbonyl that will be attacked by the inolate anion. Say carbon number 4. Excellent. That is also correct. This is your electrophilic carbon, and carbon number 3 is your nucleophilic carbon. So if we say that that means we then simply we'll have to dissect this molecule here and say we could click right here, right? Could click right there, and let us go ahead and write the the molecule from this cleavage right here. Assuming that we form enolate ion here, and assuming that this carbon number 4 is a carbonyl. Okay, so let us see here. So we have this. Okay, we have this. We have this. We have this. Okay, and then I will say I have this here. And then I have carbonyl right here. Let me go ahead and number this. Keep in mind we clip this right here. Okay, so if we do that, this is 1. Based on this numbering we did here, okay? And this is 2, carbon 2. This is carbon 3. This is carbon 8. This is carbon 7, carbon 6, carbon 5, and this here is carbon 4, and finally carbon 9. Okay? Okay, so if you agree with this analysis here, give me a happy face. Okay, in other words, this is the molecule that was used to make this compound. Okay? This is the molecule that was used to make this compound. And how do you do that? Simply have hydroxide acting as a base, and then of course you have your solvent. In this case, it could be your solvent could be water or it could be ethanol. Okay. 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 So, do you have any question on this, or you want us to move to the next question? You notice what we've done here. When you have this kind of problem, you simply take a look at the carbon-carbon double bond that is conjugated to the carbonyl. You cleave it. One of those carbon will be your nucleophilic carbon, and the other carbon will be your electrophilic carbon. So I see everybody is happy here. So let us move on. Okay. See, Lola, is your mic working? If your mic is working, can you read this question for us?
This molecule was formed by a Robinson annulation. Draw the structures of the reactants that were used.
Okay, thank you, and very good. Okay, so now what this molecule they have given us, okay, say this molecule here, okay, was formed by Robinson annulation. And now they want us to draw the structures of the reactants that were used to make this molecule. Okay, now, Robinson annulation, as you guys know, is this here. Robinson annulation is a combination of Michael addition reaction plus Aldol condensation. Keep that in mind. Okay? Actually, more specifically, it will be intramolecular Aldol condensation. It's a combination of Michael addition reaction and intramolecular Aldol condensation. Intramolecular Aldol condensation. Okay, that is what we know. That is what we refer to as Robinson annulation. Okay, so let me go ahead and draw this molecule here. This is a 6-member molecule, as you can see here. Okay, we have hydrogen here somewhere. We have a cyano group here. Okay, CH2, CH2. Then we have a carbonyl right here. You have your alpha beta unsaturated alpha beta, the carbon-carbon double bond that is conjugated to the carbonyl. Okay, so now you then have CH3 here. Okay, now keep in mind we told you that the Robinson annulation is a mixture of Michael addition followed by, maybe I should say followed by, intramolecular aldol condensation. In other words, the intramolecular aldol condensation is the last step of the Robinson annulation. So let us take a look at this molecule therefore. Since the intramolecular aldol condensation is the last step, let us look at the intramolecular aldol condensation first. So I am going to number this. Okay, let me see here. Let us say we have, let's say call this carbon 1. Let us call this 2. Let us call this 3, 4. Let's call this 5. Let's call this 6. And then we make this carbon here 7. Okay? Okay. Now, let us deal with the intramolecular aldol condensation part of this reaction. The question I have for you is, in this molecule here, which carbon will be your nucleophilic carbon? Which carbon will be your nucleophilic carbon? Okay, number 2. How many say number 2? In other words, that is the carbon from where we are going to generate our enolate anion. Okay, I think you guys may be right. Okay, say carbon 2 is your nucleophilic carbon. Okay, so which carbon will be your electrophilic carbon? Which carbon will be electrophilic? Carbon number 3. Okay, I think I will have to agree with you on that. Carbon number 3. So if that is the case, let us therefore look for the precursor for the intramolecular aldol condensation. So that means we just click right here. This carbon here becomes a carbonyl carbon. So what this tells me, since we have an hydrogen here, is this carbon here will be an aldehyde carbon right here, an aldehyde carbonyl. Okay, and of course this carbon here is alpha to this carbonyl, and that is where you generate your enolate anion. So let us go ahead and draw what we have here. So we say to be this. CH3. Okay, we say that is okay. Oh, I'm sorry about that. Let's take this back. Okay. Yeah, okay, that is this one here. Let us see this. Okay. Okay, so we have this carbonyl is here, and this is here. This, okay, so that a little better. And this is here, and this is here. And therefore you say that this is this here. See here. You see this is carbon, this, okay. Okay, this will be this. So make this hydrogen. Okay, let me go ahead and number this. Okay, based on our numbering, this will be carbon 7, this here, and this will be carbon 2 right here, and this is carbon 1 right here, and this is 6, and this is 5, carbon 5. You have the cyano group on carbon 5. Let me go ahead and put that here. You see, I also have hydrogen here. Okay, and then we say this is carbon 4. Okay, and then we say this is carbon 3. Okay, so let me draw this molecule a little better than what we have here so you can see it better. So therefore, this is what we have. Okay. 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 Now, if you agree with what I've drawn here, this is 7, 2, 1, 6, 5, 4, and 3. And of course, you have on 5, you have the cyano right here. Okay, now, so far, if you agree with this structure here, that this is what gives us this right away, give me a happy face. Okay, do you agree with this here, this structure? Okay, you agree with that structure. Okay, so therefore, very good. If you agree with that structure, let me take this out of here. Okay, so therefore, what we are saying here is that we form our inolate anion on carbon number 2, and once you generate your inolate anion on carbon number 2, that will attack this electrophilic carbon, which is number 3, and then the subsequent hydrogen transfer and then loss of water will give you a carbon-carbon double bond between carbon number 2 and carbon number 3. Okay, is that clear to all of you? If it is clear, give me a happy face. Okay, now, okay, so we have done the first part of the question they want us to solve. Keep in mind they want us to give the starting material for the Aldol condensation. Now we need to look at where did we get the Michael reaction from. Keep in mind the Robinson annulation is a combination of Michael addition followed by intramolecular Aldol condensation. So far, we have given the intramolecular Aldol condensation. So now let us now take a look at this molecule. Now, where is the Michael? So let me go ahead and let's use the same number. Let us use the same number. Now, keep in mind that in the Michael addition, you need a nucleophile. Okay, you need a nucleophile, and then you need an alpha-beta unsaturated carbonyl compound. Okay, for example, something like this. Okay, this hydrogen could be an alkyl group. So, in the Michael addition, you have a nucleophile just as we have here. This nucleophile will come in here, attack this, and this electron will go to the alpha carbon to form your inolate anion, and then subsequently we will protonate this carbon here. So you will get this. Just trying to give you a background into the, okay, no. I think I want to create more space. Take this out of here. Okay, so we have a nucleophile, and then you have a carbon-carbon double bond that is conjugated to a carbonyl. Let us assume here at this point the carbonyl could be that of an aldehyde or a ketone or an ester. So if we have this, this electron goes here, and then we have this. So nucleophile has now joined to the CH2, and now we have this. Now at this point, when you add hydrogen from your solvent, or yes, from your solvent, let us assume here that we are using ethanol for the solvent. This here, this inolate that you form here will come here and abstract the proton from the solvent. Okay, and then you form your Michael addition product. This time the Michael addition product is this CH2, CH2, and then you have this here. Okay? Okay? So that is, you form your Michael addition product that way. So now let us now come back to this here. If you take a look at this molecule, the molecule that we have here, which of these carbons here, keep in mind, we need a carbon to be the nucleophilic carbon, okay? We also need an alpha-beta unsaturated system. In other words, a conjugated system. The alpha-beta unsaturated must be conjugated. In other words, you have a carbon-carbon double bond that is conjugated to a carbonyl. So, which of these carbon here will be your nucleophilic carbon? Anybody? Which of these carbon will be your nucleophilic carbon? Because we have to form a new carbon-carbon bond. Anybody has an idea? Which carbon will be your nucleophilic carbon? Anybody has any idea? Which of these here will be your nucleophilic carbon? Okay. No, not the CN. No. Nucleophilic carbon, you have to have the inolate anion. Keep in mind your nucleophilic carbon must be, and you want to generate X. Okay. Now, no. Okay, let me ask you another question. Look at this carbon-oxygen double bond of the aldehyde, right? Look at this here. Okay? Look at this carbon number 4, carbon number 5. Okay? Look at carbon number 4 and carbon number 5. Okay? If we say we have a double bond between carbon number 4 and carbon number 5, would that be conjugated to this carbonyl? Yes or no? Yes. Okay. Now, on the other hand, take a look at this molecule here. Supposing if you look at this here, keep in mind you have to form a new carbon-carbon bond. Okay? Okay, of this carbon here, supposing we generate an inolate anion on this carbon right here. Carbon number 6. Okay? Supposing we do that. Therefore, let us look at this here. Let us say we have this right here. Supposing we have a carbon-carbon double bond here, right? And then we say carbon number 6 is your nucleophilic carbon, which tells you that you have to clip this right here. You have to clip that bond right here, right? Okay, if you do that, what do you get? We get this. So that means we have a carbon-carbon double bond. You have the aldehyde. Okay, you have the aldehyde. Then you have right here, we have your cyano right here. Okay, and of course right here you have hydrogen. Okay, so on this side also you have hydrogen here. You look at this here, you have this carbon now. This is carbon number 3. This is carbon number 4. This is carbon number 5. Okay, and of course this is your cyano here. Now, On the other hand, we then have, since we clip this, okay, so therefore, if we have carbon number 6 now becomes a CH3, okay, and that is attached to carbon number 1, which is this right here, which is attached to carbon number 2, which is this right here, which is attached to carbon number 7. Okay, let me go ahead and number this. It is a little bit more tricky than the Aldol condensation. So you have this here. This is carbon 6. This is carbon 1. This is carbon 2. And this is carbon 7. Now, supposing at this point, if you generate your enolate right here on carbon number 6, okay, if you generate your enolate on carbon number 6, that becomes your nucleophile. Okay, that becomes your nucleophile, and then that nucleophile will now attack carbon number 5, and the electron goes to carbon number 4, which is then you're going to get this right here. So this will be your carbon number 6 right here. Okay, and then of course this is your carbon number 5, and then this is your carbon number 4, and this is your carbon number 3. Now, if you see that, give me a happy face. Okay, somebody say, why can't you clip between? Okay, yes. Okay, you see that, very good. Now, somebody say, why can't you clip between the cyano group and carbon number 5? That will take you nowhere. Keep in mind that will take you nowhere. Keep in mind what you want to do. You want to form and have, for you to get a Michael addition, you need an alpha beta unsaturated carbonyl compound. In other words, the double bond must be conjugated to the carbonyl carbon. So that is the most important aspect of the Michael addition reaction. You need an alpha beta unsaturated carbonyl compound, and that is this one right here. And the only way you are going to get that is to, if you clip carbon number 6, in other words, then place a double bond between 4 and 5, and then you get your alpha beta unsaturated carbonyl system, and that is what we have right here. Okay, let me take this out of here. And that is what you have right here. This is your alpha beta unsaturated system. Okay. Okay, and then this other molecule here, the one in green, this will be the source of your nucleophile. Keep in mind what you want to do here. You want to construct your starting material so that you could get the product that you desire. This is the product that we want right here. Take this out. This is the product that we want to make. Okay? Also take this one out. So if therefore, you simply now do this. You simply now do this. Go from here, both of those molecules, to here. Now what do you need? Of course, you need your base. Your base could be hydroxide again in the presence of a solvent, and that solvent could be ethanol. So you go from here. What does the hydroxide do? You deprotonate this hydrogen here to form your nucleophilic carbon. And that nucleophilic carbon now comes in, attacks this carbon number 5 to eventually get to this product right here. And once you get to this product, right here, this here, then from here, you go to here through the Aldol condensation. Okay, is there any further question on this? Okay. Okay, so let us go to the next one. Okay. Okay, if somebody, I see a lot of you have since joined us, if your mic is working and you have not heard your voice today, can you pick up the mic and read this question? You don't have to read this red part, the part that is red. Just read the top part of the question. If your mic is working and I have not spoken to you today.
Hello?
Okay. Yeah, go ahead.
How might you synthesize the following compound using an aldol reaction? Try the structure of the starting aldehydes or ketones.
Okay, very good. That's Christopher Robinson. Very good, and thank you. Now, what they want you to do here is say, how might you synthesize the following compound using aldol reaction? Then draw the structure of the starting material. You know, this is similar to the problem we have been dealing with. Okay. To answer this question once again, let us go ahead and number the molecule. Okay, so by the way, this here is benzene. The C3, this here is benzene. So, okay. So you have benzene here, benzene here, benzene here, and benzene here. Okay, so I am going to number this. I will say this is carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. Okay. I would also tell you this, that you have two aldol condensation taking place in this process. The first aldol condensation is a regular aldol condensation, and then the second aldol condensation will be an intramolecular aldol condensation. So you do have two processes, your regular aldol condensation followed by an intramolecular aldol condensation. So what will be the product from there? I'm sorry, what will be the starting material? Anybody has an idea? How do we, okay, maybe I should be more specific. If you take a look at this molecule here, which carbon will be, which carbons will be your nucleophilic carbons? Which carbons will be your nucleophilic carbons? Taking a look at this molecule. Carbons 2 and 5. Excellent. Excellent. So therefore, which carbon will be your electrophilic carbon? Your electrophilic carbon. Number 3 and 4. Excellent. Very good. Okay. If you say that, that means we have to cleave right here. We'll cleave right here, right? Okay. So let us see, what do we get? Okay. From the top part of the molecule, we say we have this. We cleave right here. Okay. We have this here. That is your benzene. Okay, from here we also say we cleave right here, and that is also benzene right here. Okay, so this is CH2 right here, and this is CH2. You guys already told us this is where we are going to generate the nucleophilic carbon. Now, why did you pick this? It is correct, by the way. Why did you pick 2 and 5 as your nucleophilic carbon? Why did you pick 2 and 5? Is this correct? Why do you pick 2 and 5 as your nucleophilic carbon? Exactly, because those are the carbons that contain the alpha hydrogen, and from because they contain the alpha hydrogen, you could now deprotonate one of those hydrogen to form your enolate anion. Very good. So you could form enolate anion here, and then you guys also told us that carbon 3 and 4 will be your electrophilic carbon, which means that they must be this. Electrophilic carbon means that the carbonyl carbon. Okay. Of course, once again, okay, benzene is here. Benzene is here. Okay. So if you have this attacking this, And okay, subsequently you get the Aldol condensation right here. Then you lose the water to form a carbon, to form your carbon double bond. So therefore, let me go ahead and number this. So this is your carbon number 2, carbon number 1, carbon number 5. And here is your carbon number 4 and your carbon number 3. Okay? So the question they ask us to give the answer to is to give the starting material. So therefore, this is the starting material without the inolate allyl. Okay, if you agree with that, give me a happy face. Okay, so we say compound, yes. Say compound, let us call this compound A, and compound B are the starting material. I think all of you agree with that. Very good. Okay, so let us move on. Okay, let us see here. Okay, just give me 1 second. Let me make this a little smaller so that it could fit into the screen. Okay. If I have not heard your voice today and your mic is working, can you go ahead and read this question for us? Okay, I do know. Okay, Jaconda, go ahead and read this for us. I know your mic is working.
What enol product would you expect to obtain from intermolecular Aldol condensation of 3-methylheptane-diol?
Very good, and thank you. Okay, so they say what enol product? Okay, once again, I want to remind you, an enol is a molecule that contains a carbon-carbon double bond and a carbon oxygen double bond, particularly of a ketone or aldehyde. Okay, so we call those type of molecule enol. Okay, so therefore they say what enol product will be you expect to obtain from intramolecular Aldol condensation of 3-methyl heptane diol, which is 2 aldehyde on opposite end of the chain. Okay, so let us look at that molecule. So we have this molecule here. So they are also testing your knowledge of nomenclature. Okay, 3-methyl. So you have a methyl group in the 3 position. That is 4. That is 5. That is 6. And then, of course, you have a carbonyl of an aldehyde at the end. Also, let me be consistent here. Okay, this is this here. Okay. Okay, that is 1, 2, 3, 4, 5, 6, 7. Okay, so let me go ahead and number this. 1, 2, 3, 4, 5, 6, and 7. Okay, so now they want us to see what enol product would you expect to obtain from the intramolecular Aldol condensation. So let me go ahead and write that in a way that we can see and relate to a given product. Supposing we have it this way. Okay, so we have this. 1, 2, 3, 4, 5, 6. Okay, we then say 7. Now, okay. Okay, so let us number this. This is 1, 2, 3. So a methyl is here. Okay. Now let me go ahead. Carbon 1, 2, 3, 4, 5, 6, and 7. They say heptane dial. In other words, you have 7 carbon atoms. Okay. Now, the question is, what product are we going to get from intramolecular aldol condensation? It could very well be more than one product. So let us see here. Okay, let me ask you a series of questions. Which of these carbon could potentially be a nucleophilic carbon? Which of these carbon could be a nucleophilic carbon? In other words, the carbon from where you are going to generate the enolate anion. Give me the number 2. Okay, very good. So you want us to use 2 for your nucleophilic carbon. So if you do that, very good. That is possible. If you do that, what would be your electrophilic carbon? Okay. If okay, 7. Very good. So therefore, just to be consistent with what I have been giving you, electrophilic carbon is this color here. Okay. Okay. So therefore, you say the nucleophilic carbon is carbon number 2, and electrophilic carbon is carbon number 7. So we join them together. Let's see. Okay. Okay. So this how many carbon do we have in this ring? If we do that, how many carbon we have in the ring? You say 6. Okay, 1, 2, 3, 4, 5, 6. Excellent. Okay, so let us do that. So we say, let us call let me begin, okay. This here, let us call that A, compound A, the one with that color. Let's call that compound A. So compound A will give us 6-member ring. That's what you guys are telling us. Okay. I am going to start numbering based on what you just given me, since you want to join 2 and 7. So I say this is 2, and therefore this is 7. Okay. So if you say that is 2 and that is 7, now follow me very closely now. Okay, this is 2 and this is 7. Let me get this out of the way. Okay. If that is the case, therefore, carbon number 1 is attached to, oh no, save my pen. Carbon 1 is attached to carbon 2. Okay, which is this one right here. Okay. Therefore, if that is the case, that means we must have a carbon-carbon double bond between 2 and 7. So far, if you follow that so far, give me a happy face. Okay, very good, very good. Now, if that is the case, so let us go ahead and number this carbon. We say this is carbon 1. We say this is carbon 2. Therefore, this is carbon 3 right here. That means this is carbon 4. That means this is 5. And then this is 6, which was attached to carbon number 7. 6. So on carbon number 3, you must have a methyl group. Okay? So that is a possible product. Okay, do you see that? If you see that, give me a happy face. Okay, so this compound A is a possible product. Okay, if we use this here, okay? Now, let us, okay, give me another possibility. Okay, we said that is a possibility. Let me take this out. Okay, give me another possibility. Which would be your nucleophilic carbon again? 6. Somebody says 6. Okay. Somebody says 6. Let us continue the tradition of using pink for nucleophilic carbon. Oh, I messed that up. Okay. Okay, and then I want to also take this off. Okay, I'll put that back here. Okay. Now, continuing the tradition of using pink for nucleophilic carbon, you say we want to use 6 for nucleophilic carbon. Okay, very good. So 6 is nucleophilic carbon. And then you say you want to use 1 for electrophilic carbon. Okay, very good. Okay, so therefore 1 for this here. So what do we want to do? We want to join this. Okay, how many carbon in that ring? How many carbon atoms do you have in that ring if you join 1 and 6? If we join, okay, 6-member ring. Okay, so that's a 6-member ring molecule. So therefore, let us say again, okay, we call this B. Okay, oh, another 6-member ring. Okay, if we do that, let me go ahead and say, since you say this is carbon 1, and you say this is carbon 6, so therefore, on carbon 6, you must have the aldehyde. Okay, if that is the case, this is carbon 1, this is carbon 2. Let me change the color of my pen. Carbon 2, carbon 3, carbon 4, carbon 5. So that means on carbon 3, once again, we have a CH3. Okay, we have a CH3. So now, where is the double bond? Where is our double bond? Where is our double bond? Keep in mind, we join carbon 1 and 6. Excellent, carbon 1 and 6. Okay, very good. Since those are the 2 carbons that we joined, so therefore our double bond will be between carbon 1 and 6, which is this here, 1 and 6. Okay, so now we also have another product here. Okay, if you agree with that, give me another happy face. Okay, okay. Is there any other possibility? Yes or no? Any other possibility? No, no, because these are the only places where we could generate the nucleophilic carbon and the electrophilic carbon. So therefore, the product that you are going to get from this reaction, this molecule here, you get 2 products, A and B. Okay. Okay. So if there is no question, let us move to the next one. Maybe we do a couple more questions before we leave. It is about 8:58. Okay, about this one here. This is very good. This is similar to the last one. Okay. Lorna, go ahead and read this question for us. Okay. Okay. Christopher, go ahead and read this question for us.
Draw the organic product or products of this intramolecular aldol condensation reaction.
Okay, very good, and thank you. Okay, so now they want us to draw the organic product from this this molecule here. This is similar to the last one. Okay, so let us to do that. Okay, of course they say intramolecular aldol condensation. Let us go ahead and number the carbon again. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. For you to be able to draw this, okay, let me ask you again, which is your nucleophilic carbon? Oh, okay. Nucleophilic carbon is 8. Okay, you want to use 8 for nucleophilic carbon? Okay, very good. Because you could generate enolate ion here. Okay, oh, you say 1386. Okay, yes. I think you guys already have an idea what this is. So you say you could use carbon 1, carbon 3, carbon 6, and carbon 8. That is correct. Each one of those carbon could potentially give us the enolate anion. And of course, which would be your electrophilic carbon? Which will be your electrophilic carbon? Okay, 7 and 2, exactly, 7 and 2. So your electrophilic carbon will be 7 and 2. So you could do all kind of combinations here, okay? So if you want to use, say we want to use 8, that means you want to join 8 and 2. If you join 8 and 2, how many carbon are you going to have in the ring system? How many carbon are you going to have in the ring system? 7. Okay. So therefore, let us go ahead and draw a 7-member ring. Okay. So let us start off by saying that we say this is let us say this is our carbon number 7. It's our carbon number 7. So therefore, if that is our carbon number 7, and we say this is our carbon number 8 right here, okay, what that tells you therefore is that you must have a methyl group attached to this. Okay, therefore this must be your carbon number 2. Okay, let me change the color there. So this must be your carbon number 2, because what are we doing here? We are joining carbon 8 and carbon 2. Okay? An electrophile is a carbon that will attract a nucleophile. Okay. So therefore, so we have carbon we have carbon 8 and 2, we are joining them. Okay, that means therefore the carbon-carbon double bond will be between carbon 8 and 2. So we have this. I will do this one and then I will leave the rest for you guys to complete. So we could then have this here. So we have a carbon-carbon double bond between carbon 8 and carbon 2. Okay, so therefore, that means also on carbon 2, we must also have okay, so let us go ahead and complete the numbering here. So we say, keep in mind we say this is carbon 7 right here. So therefore, this is carbon 6, this is carbon 6, this is carbon 5, this is carbon 4, this is carbon 3, of course, this is carbon 2 right here. Okay, and then of course that joined to carbon 8. So that means this is carbon 9, and here is carbon 1. Okay. So this is one of the possible products. So I am going to leave you guys to now finish up the rest of this problem by simply joining together the nucleophilic carbon and the electrophilic carbon. And then you form a carbon-carbon double bond between those electrophilic carbon and the nucleophilic carbon. Keep in mind, in this particular instance, you only have 2 electrophilic carbon, and those are the carbonyl carbon. Carbon 2 and carbon 7. Okay, so let us see. I want us to do a mechanism problem. This should be fairly easy for all of you. Okay, now before we leave, let us do this reaction mechanism here. Okay, in order to test your knowledge of your true knowledge of the inolate anion chemistry. Okay, now in this molecule here, what they want us to do is to provide the mechanism, for the transformation. Provide the mechanism for this transformation. We are going from this molecule here, I would say this is molecule A, and this is molecule B. Okay? If we are going from molecule A to B, okay, and they want us to give the reaction mechanism, this is fairly, this is a lot more than what you might think, but you guys can do this, okay? I will give you a hint. The first thing that you do is a Michael addition. Okay? You do a Michael addition, and then once you do your Michael addition, and then, okay, well, let's do the Michael addition first. Okay? I'm going to number this carbon here before we go to the next step. Let us number this carbon. Let us say 1, 2, 3, 4, 5, 6, and 7. Okay? I've already told you we are going to do a Michael addition. Okay? And we have hydroxide here. I'm also going to tell you that the hydroxide could act as a nucleophile this time. Instead of acting as a base, it could act as a nucleophile. So therefore, what do you think is going to happen? What does the hydroxide do at this point? Before I told you that we are going to do a Michael addition. Okay, what carbon does bind to carbon number 3? Excellent, excellent, very good. So this hydroxide, therefore, since we want to do a Michael addition, it will attack carbon number 3, and in so doing, this pi electron go here, and then what do we get? We get this. Okay, so we have a 5-member ring. We have the carbon-oxygen double bond. We have this here. We have the OH as attack, right? And then we now have, once you do that, the pi electron. Can you guys hear me? If you can hear me, give me a happy face. Can you hear me? If you can hear me, give me a happy face.
We can hear you. You have to scroll down.
Oh, okay. But I'm sorry about that. Yeah, thank you. Okay, good. Okay. We had a temporary loss of our internet service there. Okay. So what happens here? We have this. This hydroxide comes in, attacks carbon number 3. The pi electrons go to carbon number 4, and that is what we have. So we form this inolate anion. And then what happens? We are at this point. Okay, does anybody know what could happen here? Okay, well, there will be a proton transfer. There will be a proton transfer. You have this here. Okay? Proton transfer to this here. And at the same token, this here, well, let us do one step at a time. Okay? Let's say this electron comes to oxygen. I want to do one step at a time so I do not confuse you. So at this point, you form this. Okay, now keep in mind now we have, this is now protonated. Now we have this here, the alkoxide anion. Now we have this here. Now guess what is going to happen at this point? What do you think will happen at this point? Let me go ahead and continue the numbering here. We still have our carbon number 1 here, carbon number 2, carbon number 3, carbon number 4, carbon number 7, carbon number 6, carbon number 5, and carbon number 4. Okay? Now, what do you think is going to happen? I will give you a... Okay, yeah, just... Okay, what do you... Oh, you said shift. Very good. Okay, what will happen before the shift? What will happen before the shift? What will happen? We have this alkoxide here. What will happen before the shift? Okay. No, we did the deprotonation already. Before you get a shift, what is going to happen? Okay, what will happen here? We are going to reform a carbonyl. This carbonyl, we're going to form a carbonyl here, and once you form that carbonyl here, therefore there is going to be a shift. Okay, you get a shift. What you get is going to form the enolate anion. So therefore, this is still here. Okay, so this will be this one here. This is the one that is broken away. And then the enolate is on this right here. Okay, and of course we have, this is still attached to 3. And draw it so that we could see that better. See, attached to that. Okay. So now this is your 1. This is your 1, your 2, your 3, and this here is your 4. Okay. So now you form this enolate anion here, which could then, this enolate anion now could now be protonated. They say you have a solvent in here. That will now be protonated by your solvent. You now pick this up. It comes here. And therefore you get this. So now you get this here. This here. This here. This here. This here, this here, this here. Okay, now you form this molecule here. Now, the interesting thing that now happens, keep in mind what have we formed now. We have essentially opened up this molecule to now form this diketone right here. Now, keep in mind, this is what we want to explain. How do we form this product right here? Okay, so let me make some space. Okay, how do we form that product? So we now have this. What we now form is this, okay, this and this. Okay, so we are going to number. This is our carbon 1, carbon 2, carbon 3. Okay, this was our carbon 7, carbon 6. And this is our carbon 5 and our carbon 4. Okay, the same thing right here. 4, 5, 6, 7, 3, 2, and 1. Okay. Now, let me now ask you this. Keep in mind, this is where we want to go. If you take a look at this molecule now, the way we have this here, follow this very closely. Take a look at this molecule that we have formed here as a result of opening of this here. If you look at this, in order for us to get here, if you look at this very, very closely, okay, which carbon here will be, you are going to get a nucleophilic carbon, and then you are going to get an electrophilic carbon. Which carbon in this molecule will be your nucleophilic carbon, and which carbon will be your electrophilic carbon? If you take a look at this here, if you take a look at this right here, Okay, 2 is nucleophilic. Okay, excellent, excellent. And which is your electrophilic? In other words, you want to form enolate right here. You want to form the enolate right here. And 5, excellent. Okay, if you do that, that is correct. Okay, let us now see. We join 5 and 2. So what will be the number of carbon in the ring? That is 1, 2, 3, 4, 5. Okay, and therefore we have a 5-member ring. That is excellent. We have a 5-member ring. Okay, we have a 5-member ring. We say carbon number 2. Carbon number 2 is joining to carbon number 5. Okay, if that is the case, therefore carbon number 3 will be here. Carbon number 3 will be there. Now, if carbon number 3 is there, therefore you have a carbon-carbon double bond between carbon number 2 and carbon number 5. And on carbon number 2, you have a methyl group. And carbon number 5, right here, you also have a methyl group. Okay, carbon number 5, you also have a methyl group. Now, if you take a look at this molecule here, that is the same as this molecule. Look at this molecule that we've just given you here. This here and this here, they are the same molecule. So the point we made here, I know this is a very complicated problem. What this simply was testing here is your ability to move electrons around, of course, and also your ability to recognize the nucleophilic carbon, electrophilic carbon in an Aldol condensation. So this is a very, very interesting problem, because you started with a Michael addition, opening up this to form this here, and once you form this, then you are then able to then use this to generate this product right here. So it is a fairly complex problem. It does take understanding of the reaction mechanism. Okay. Okay, so I think we have come to the end of today's session. Is there any question before we go? Okay, we have spent about 1 hour 20 minutes. Okay, if there is no question, I will stay around for another 5 minutes for those of you who may want to ask me additional questions. And for the rest of you, I will say enjoy the rest of your evening, and I will try to post this material by tomorrow morning. So see you next Tuesday.